Hi students, so let us try to understand few more MOSFET basics in these videos. In the first question of AEC and ME, it says that in a MOSFET, if W by L ratio increases to get desired current, it requires lesser VGS. So now what is this question? Because we have been given the options like yes, the statement is correct. The second option is no, VGS required is more, and third one is no, ID is independent of VGS, and the fourth answer is don't know. So let us try to see what is that we are looking for. We are actually looking for something like this. Just a minute. So we have the MOSFET. So let me write the MOSFET structure, the way how it looks. Of course, we have this. This is MOSFET looks. So this is gate structure. This is source. This is drain, and we know that this is length of the transistor, and this happens to be the width of the transistor. So we also know that it operates in three different regions, that is linear cutoff and saturation. Okay, what is asked now is, so in a MOSFET, if W by L increases to get the desired current, it requires lesser VGS. So let us try to write the expression for ID in linear region. One second. Okay, now we know the expression for the current if the MOSFET is operating in saturation region is given by half Kp W by L VGS minus VTO whole square. This is when it is in saturation. When it is in linear region, it is given by half Kp at W by L. It is 2 VGS minus VTO into VDS minus VDS square. So this is the expression for the drain current in saturation region. Whether the MOSFET is operating in saturation or linear region, from this equation we know that ID is proportional to W by L, and of course it's also quadratically depending on VGS in case of saturation, and it is linearly with respect to VGS in linear region. Okay, keeping this in mind, so let us try to see the question here. In a MOSFET, if W by L increases to get the desired ID, it requires lesser VGS. So the question now is, suppose if you are looking for a certain value of ID, if you increase the value of W by L, so assume that this is fixed. Suppose if you increase the value of W by L, so naturally to get a desired current, if W by L increases, so I can able to achieve the desired ID with an increased W by L by giving lesser VGS. So the amount of lesser VGS depends on whether it is in saturation region or linear region. But anyhow, to get the desired current, if W by L increased, it requires a lesser VGS. The answer is yes, the statement is correct. So let us go to statement again and then try to reconfirm that the statement is correct. In a MOSFET, if W by L increases to get the desired ID, it requires lesser VGS. The statement is correct. Let us see this now. So the second question, channel length modulation lambda in a MOSFET has larger value for lower channel length. So let us try to understand what is this lambda value and its channel length, okay, how it depends on. So let us go back to this again. Let me again write this structure of the MOSFET a bit more clearly. I am just exaggerating this channel length. So this is the length of the transistor. Of course, this is the length of the transistor. Assume that you have something like this as the channel here. So this is an ideal channel, whereas a typical channel we're going to see at the drain end. Okay, this is okay. We know that if it is P minus, this will be N plus, this will be N plus. If this is drain side, if this is source side, so at the drain side the channel will be get pinched. Suppose if you further increase the value of VDS when the channel is existing, for a larger value of VDS, the channel shrinks here. Channel will going to pinch off. So this is my L effective. So this is L effective. So now assume that length of the channel, because usually we know that this will be a very small quantity. So that is this pinch region from here to here will be a very small quantity. So let us assume that length of the transistor is something like 1 micrometer, and let us consider this is L1. So L2 is, assume that it is like 100 nanometer. So these are the two transistors having. So let us assume that the reduction in the channel length is something like, let me say it as L double dash. So L double dash is the reduction in the channel length. So let us assume that L double dash is equal to something like 2 nanometer. So now when this reduction, of course this shrink in the channel is, if it is 2 nanometer, then what is L effective? L effective is equal to 1 micrometer minus 2, let me take it as 20 nanometer. So it is 20 nanometer. So how much will be this? So we know that 1 micrometer is nothing but 1000 nanometer. So this is 1000 minus 20, which is like 980 nanometer will be the L effective. Now again, considering the same L double dash as 20 nanometer, then what is L effective when the channel length is 100 nanometer? Can you say it is 100 minus 20, which is 80 nanometer? Now let us see the percentage change in that. So we know that, so from 1 micrometer it has changed to 980 micrometer. So from 100 nanometer it has changed to 80 nanometer. So comparatively the change is very less here, the change is larger. So the percentage change from 1 micro to 980 micro is very small compared to 100 nanometer to 80 nanometer. So in order to have the effect of this channel length modulation felt in your transistor for shorter channel length, we will be representing, if I represent this by lambda 2 and this as lambda 1, naturally lambda 2 should be far greater than lambda 1, because the change in the channel length, percentage channel length is more when the channel length is lesser. So when the channel length is lesser, the channel length modulation effect will be more and more for a shorter channel. So now the question is, now how do we account for this in the expression of ID? Again, for ID saturation you write it as half Kp W by L. This is now again VGS minus VTO whole square 1 plus lambda VDS. So this is that effect of channel length modulation incorporated in the drain current expression. So naturally for shorter channel length transistor, lambda will be more. Typically lambda is equal to 0.1 micrometer. Lambda is equal to 0.01 micrometer. So suppose if I say this is okay, let me say it is L1, L2. If I say this as Lx, Ly, so can you tell me which length of the transistor will it be more, whether Lx is more or Ly is more? So looking at this, okay, let me write this as lambda 2. Now since lambda 2 has got very less change in this, so naturally this Ly should be a larger length compared to this, because it is having very less impact of channel length modulation on the current. So naturally Ly is far greater than Lx. When the value of lambda is more means its channel length is less, or I can write Lx is having a very less channel length compared to Ly. Of course both are correct. So if you go back to this, channel length modulation factor lambda in a MOSFET has a larger value for lower length channel. So that is very evident here. Of course, what is the statement? The statement is correct. Now lambda certainly depends on what is the length of the transistor. If the lambda value is, suppose if the length of the transistor is lesser and lesser, then lambda value is more and more. So of course it is not depending on the width of the transistor, it purely depends on the length of the transistor. Fine. Okay, let us try to find out in this third question. It is a biasing circuit is given, a VGS of 0.6 is applied, and we have been given the value of Kp and VTO, W will also given, and RD is given. And in the above circuit it is asked to find if the value of RD changes from 1.5 kilo ohm to 500, from 1k if it becomes 1.5k, from 1k if it becomes 500 ohm, does the drain current vary? So naturally in a first go we think that okay, as the resistance changes, naturally current has to change, but it may not be the case of this circuit, because we want to check whether the MOSFET is there in linear region or in saturation region when the value of RD is 1k, 500 ohm and 1.5k. So for that, let us rewrite the circuit and then try to find out what is the region of operation of the MOSFET. Meaning, if the MOSFET operates in saturation region for all the three values of RD, then ID will not change. Suppose if the transistor enters linear region for larger value of RD, then the current will change. So let me just write the circuit here. So what I have the circuit now is, this is the circuit what I have. This is 1.8 volt. RD is given as 1 kilo ohm. This is 0.6 volt. WL is taken as 50, and Kp is assumed to be 200 microampere per volt square, and VTO is taken as 0.4 volt. So let us try to find out whether the MOSFET is in linear region for this particular value of RD itself or not. So we know that ID is given by half Kp W by L VGS minus VTO whole square, which is nothing but, let me get the calculator, just a minute. Okay, now we can see the current happens to be, okay, now it is 100 minus 6 into 50 into 0.2 whole square. The current is 200 microampere. So ID happens to be 200 microampere. If it is 200 microampere, we know that okay, how much is VDS? VDS is actually equal to, so if I name this as VDD, VDS is actually this voltage. Okay, let me say it as VD. So VD is given by VDD minus ID into RD, which is nothing but 1.8 minus, it is 0.2 milli multiplied by 1K. Okay, this will go off and you end up with 1.6 volt as VDS. So since VDS is 1.6 volt and looking at this, VGS is equal to 0.6, VDS SAT is equal to VGS minus VTO will be 0.2 volt. Since VDS is far greater than VDS SAT, so MOSFET is in saturation. MOSFET is in saturation. Now let us find out what is RD max we can have. So what is this RD max? RD max is the maximum value of RD to keep the MOSFET in saturation. So that can be found by equating this VDS to 0.2 and this is VDD minus 0.2 into RD max. Therefore RD max is equal to, so we know that it is VDD minus VDS minimum by 0.2. Okay, sorry, 0.2 milli. This is 0.2 milli. So this is actually 1.6 by 0.2 milli. Now that happens to be within 8K. 1.6 divided by 0.2 exponential minus 3. This is 8 kilos. Of course, what does this actually mean is, if the value of RD is equal to even 8 kilo ohms, the MOSFET will be in saturation region. Meaning, if this is VDS, if this is ID, if I write this as the characteristics, if I write this as the characteristics, how it goes, this is for a VGS of 0.6 volt, if this is 0.2, now this will be 200 microampere. Now if the value of RD is 1 kilo ohm, if RD is 1 kilo ohm, I know that VDS happens to be 1.6 volts. Assume that this is 1.6 volt, this VDS. If RD is equal to 1.5K, then how much will be this? So 1.5K is actually 0.3, it will be 1.5. It will be 1.5. If it is 500 ohm, so this is for RD is equal to 1K. This is for RD is equal to 1.5K. We know that when RD is equal to 500 ohm, so it's actually okay, 1.8 minus 500 into 0.2 exponential minus 3. It's 1.7. It's 1.7 volt. So for all the values of RD, which is 1K, 1.5K or 500 ohm, the current is 200 microampere. Current is 200 microampere because all these values of RD are far less than 8 kilo ohm. The MOSFET is in saturation because this is the saturation region. So the answer for this question is in the above circuit, if the value of RD changes from 1K to 1.5K or 1K to 500 ohm, the current varies or not. So no, current will not vary. The answer is C. Does the drain current varies? No, the drain current doesn't vary. Okay, let us see the next question. Okay, in the same circuit, suppose the value of VDD has increased from 1.8 to 2.8 volts, does the drain current increase? Now the question is this. Now instead of this as 1.8 volt, if I make this 2.8 volt, does the current increase? So now if you can see this current, which is 200 microampere, is independent of this VDD. So whether it is 1.8 or 2.8, as long as the MOSFET is in saturation region, the current is 200 microampere only. So whether it is 2.8 or 1.8, the current will not change, because the MOSFET will not change its current as long as it is in saturation region. So the answer for the third question is no. In the above circuit, if VD is 2.8, does the drain current increase? The answer is no, the drain current will not increase. Okay, hope this will help you. Thank you.